Imagine you're preparing for a massive, high-stakes exam. You have a towering stack of textbooks, flashcards, and past quizzes, and a limited amount of time to make sense of it all. You could take the slacker approach. You skim a few chapter summaries, ignore the details, and hope the test is easy. You're putting in very little effort, but you're also likely to miss the big ideas. Or you could take the anxious overachiever approach. You memorize the exact answer to every single practice question. You feel ready until test day, when the professor changes the names and numbers in the questions, and you fail because you only memorized those specific examples instead of learning the logic. Machine learning algorithms aim to grasp core concepts so they can successfully handle new situations. They use the data they have to prepare for the data they haven't seen yet. Every time we train a model, we assume there is a true, meaningful relationship hiding underneath a layer of random, messy, real-world noise. Our goal is to find that smooth path. As the person building the model, you choose how flexible it is. You can restrict it to drawing a stiff, straight line, or you can give it the freedom to weave a highly complex, wavy curve. But that choice is a balancing act. If you pick the wrong level of flexibility, your model will fail at predicting what happens next. Picking the wrong complexity level results in one of two specific problems: underfitting or overfitting. Let's look at underfitting first. This is our slacker student. An underfit model assumes the world is incredibly simple, and it's too rigid to see the actual patterns in the data. Look at this graph. The dashed green line is the true pattern, but we forced our model to use a straight pink line. A straight line cannot bend to match a curve. This consistent gap between our straight line and the true curved path is called bias. It's a structural error caused by making overly simple assumptions. Because this is a limitation of the straight line itself, throwing more data at the problem won't help. The model just doesn't have the capacity to learn anything more complex. A model with high bias is essentially blind to the patterns in front of it. It makes huge mistakes on the data you train it on, and it continues making those mistakes on future tests. Now let's look at the other extreme, overfitting. This is our anxious memorizer. An overfit model is so flexible that it starts treating every random glitch and piece of noise as if it's a crucial fact. Here is a chart showing a model with too much freedom. Instead of finding a smooth path, these blue lines snake wildly up and down to touch every single training dot perfectly. Because it's trying so hard, if we give it a slightly different set of dots, it draws a completely different shape. This extreme instability is what we call variance. When you introduce new data, this model crashes. It tailored itself so precisely to the random noise of the past that it completely missed the actual trend. High variance models are deceptive. They appear perfect during training, but they fall apart the moment they're applied to the real world. You can't just eliminate both problems at once. Decreasing your bias naturally increases your variance, and locking down your variance increases your bias. They trade off against each other. This chart maps the error. As model complexity increases, training error drops. This red line is shrinking bias. But unseen test error shoots up as the model memorizes noise. Combined, your total error, the purple line, forms a U-shape. That gold circle at the bottom of the U-curve is the sweet spot. It's the perfect level of complexity that balances underfitting and overfitting. You'll notice the error never hits zero. There is always a baseline level of randomness in the world, like measurement glitches, that no model can predict. We call this the irreducible error. The ultimate goal is finding that lowest possible point on the curve to minimize mistakes on tomorrow's data. Diagnosing these problems is straightforward. If your model performs poorly on both your training data and your test data, it's too simple. You have a bias problem. If it has a 99% success rate in training but fails the real-world test, it's memorizing noise. You have a variance problem. To find the sweet spot, we use a tool called cross-validation. By repeatedly chopping the data into different chunks, we can simulate the future and see how well the model works on data it hasn't seen before. Closing this performance gap between the practice data and the real world is how we ensure our models are actually learning. But what if you have too many detailed pieces of information, the individual features of your data, and your model is forced to overfit? You can't just delete valuable details to make the model simpler. To solve this, we use a tool called regularization. It's a mathematical penalty that forces complex models to ignore the noise and behave more simply. We'll cover exactly how Ridge and Lasso regression solve this problem in the next video. Hit subscribe so you don't miss it, and thanks for watching.